Welcome to the course Building Robust and Secure AI Systems that belong to the section Trustworthy AI of the Trustworthy and Explainable AI MOOC being developed in the context of the Enfield project. This is the third unit of the course, which is called Real-World Scenarios. I am George Pathoulas and I'm an associate professor at the Department of Information Security and Communication Technology in NTNU, Norway. There have been many research efforts that have proved that all the attacks we discussed in previous units are practically applicable into everyday systems. So we've seen approaches from researchers that try to use accessories like hats and glasses, and through the use of those they try to fool a face recognition system. Face recognition systems are based on machine learning models which are susceptible to attacks like adversarial examples, and this more or less aligns with what we discussed in the previous units. Researchers have also proved that model stealing is feasible via APIs. So attackers were able to reconstruct a functional replica of the original model by observing the output of the model when it's being presented with a high load of specifically crafted inputs. And on top of that, we've seen data poisoning attacks that happen against production machine learning pipelines, where attackers are able to inject labeling inconsistencies and carefully craft trigger patterns into the training dataset, and thus the model that is being trained on such datasets becomes insecure as it contains backdoors that can be activated through specific triggers. All these research findings have led the AI community to the conclusion that production systems need to be protected. And this is reflected to a number of different examples that will follow, in which major providers of AI technology have been using defenses as the ones we discussed in Unit 2. The first example comes from Google and how it tries to enhance its keyboard, the Gboard, that is being used in mobile devices with Android operating system. Such keyboards have a text prediction system in which they try to use what the user has already typed in order to predict the most probable word that the user wants to type just after that. By observing the series of words that users type in their keyboards, it is feasible to train a model that is capable enough in order to make such predictions in an accurate way that is helpful for the user. But Google, instead of gathering all such data centrally and trying to train a model which then would be integrated in the keyboard, opted for using federated learning. This means that text that users type never leaves their devices. The data is used to locally train a model, the updated weights of which is then sent centrally to Google, and this continues for many rounds. And on top of that, in order to better protect the privacy of its users, Google has also added differential privacy. Thus, it does gradient clipping, noise addition, and secure aggregation, so that even by the weights that are being sent from the user's devices to the central server, to not be feasible to extract any personal sensitive data from text that users type. A second example relates to query monitoring against model extraction. This example comes from Amazon Web Services, which offers a number of machine learning models through machine learning API services. And there the vulnerability that is aligned with what we already discussed is model extraction. So an attacker can potentially send a large number of queries and observe the input and the corresponding outputs, and from that try to create a replica of the model that is proprietary, that is closed access, and AWS does not want to reveal. In this case, AWS has used rate limiting, so they use strict limits on the number of queries per second someone can send, the total daily queries that someone can send, and limits related to bursts of queries. AWS also does query anomaly detection, so they observe the activity and they try to detect suspicious patterns typical of model extraction. And finally, they also try to limit the responses they give, so they tend to not give, for example, the probability for all the classes for a data point, but only the class with the highest probability, thus trying to limit the feasibility of a model extraction attack. The third example relates to adversarial examples and comes from Microsoft. Microsoft uses an advanced robustness toolkit for its machine learning system to protect them against adversarial attacks. This toolkit is being integrated in the Azure machine learning pipeline that Microsoft uses. The adversarial example threads relates to crafting inputs in a way that they can fool a model. Microsoft tries to use adversarial training, so their models are exposed and trained on adversarially generated inputs, similar to the ones that an attacker could use. They also try to do input pre-processing, like feature squeezing and input denoising, in order to make the input that they receive less capable in terms of adversarial examples attack. And finally, they monitor their models and try to do robustness testing, so they are sure that at each time their models behave as expected. The course is concluded with a reference to future challenges that we face with regards to AI security. AI security is a field that has been around for years, but due to the recent hype around AI and the developments in AI technology, has been very popular and has seen a lot of demand. First of all, we have to understand that most of the methods that we have introduced in this course against such attacks may bring a performance penalty. It is feasible to robustly train a model, but this is a heavier process than just train the model and ignore adversarial examples. So we have to balance between robustness and performance. Foundational models bring a new set of challenges. Those are models that by default are trained on vast amounts of data, and this makes it very difficult to apply input validation approaches that we have discussed, so other methods are needed there. The machine learning supply chain is an important factor in the security discussion. The end result that we build in our machine learning pipelines is relevant to pre-trained weights that we may use, third-party datasets or open source libraries, and all these artifacts may hide different security risks. Finally, one challenge we have is that it is needed, as AI systems are being employed in safety critical applications, to be able to ensure that our models will pursue their intended objectives throughout their lifetime. And this is a challenge that we are still facing and trying to find ways to fix it. So the key takeaways from the full course, all 3 units of the course, are the following. First of all, we are facing a new threat model. Machine learning is a process, is a pipeline of different steps. It's not just a system, so we need new security approaches to to protect such systems. We for sure need to add robustness to AI systems by design. It's very difficult to increase the robustness of a system after it has been deployed. We're facing a challenge with the full life cycle coverage of the project. It's difficult to maintain the security of a machine learning system if you are not there throughout the lifetime of the model, the whole duration in which it is used. The other key takeaway that we should not forget is that we're talking about a fast-moving field. What we discussed today about AI may be relevant in some years from now. So the security approaches we use shall be adapted as AI technology progresses. And with that, we conclude with the third and last unit of the course, and I would like to thank you for participating to it.